Do I need to speak into this, or can I just talk like that and you hear me? It doesn't really work, does it? I just use the microphone, right? Everyone can hear me? Okay, good. The text is readable. It's going to be about this size, right? So yeah, let's start with a little bit about me. So I'm Viktor. I'm currently the deputy director of the InCipher program in Imperial, which is based in Singapore, this InCipher program. Before that, I was working in industry a little bit. I was working as an AI researcher on intelligent medical information systems and hospital information systems. I was a lecturer at the Uni of Manchester at the Department of Computer Science until around 2022, where I still maintain my honorary affiliation. And before that, I was sort of doing a couple of different stints across the industry as well. My PhD is from the Uni of Manchester. My master's and bachelor's is both from the Uni of Passau, which is a university in Germany, all in computer science. And yeah, my research areas are sort of in the order of as they appear today and are relevant to me today. Privacy-enhancing technology. Generally, I would say I work on NLP applications, mostly focusing the clinical or medical domain. And looking at NLP and language technology, so LLMs nowadays, of course. And before that, and sort of as a leg in parallel to that, I'm working on AI and NLP evaluation, benchmarking. What can we talk about, or what can we tell about the abilities of language technology and AI technology nowadays, and how reasonably and how reliably can we do so. So today we're going to talk about LLMs. The course or the lecture is called LLM Foundations. And well, one of the questions is, so what are large language models? And depending on who you ask, you might get different answers. My favorite answer to this, LLMs are bullshit machines that very well apologize. That's from Daniel Stenberg, who is the maintainer of curl. And he has his reasons to believe so. But if you ask other people, well, you know, the traditional people would say these are very good text representation tools. Others might say, well, these are essentially autocomplete machines, right? They can predict the text in a sentence based on what the next word is going to be very well. Others might say, well, you know, they're quite helpful assistants. So whatever I use, your favorite assistant of choice to do your favorite or least favorite task for you, right? Or you could also say they're sort of general purpose technologies, and we're going to see how this pans out later today with the second part of the Foundations talk. So the point is, depending on sort of who you ask and how you look at it, there's a difference in interpretation, difference in scope, and of course, the more down we go, the bigger the scope and the ambition becomes. And I guess the correct answer is probably that LLMs are to some extent all of those. So what we will do in this first lecture is we're going to explore how these lower level definitions of text representation and next token prediction essentially compose and enable the higher level aspirations of being helpful assistants or general purpose technologies. So the talk outline today is we're going to start with what are actually words, and this is essentially a primary tokenization. We're going to talk about text representations, embeddings, and language modeling. We're going to talk about some historical architectures to do so. We're going to briefly cover transformers. I understand you've already learned about transformers in the first day of the winter school, right? Then we're going to talk about how we can train these transformers to perform the language modeling task. We can see how we can then use these trained models to perform inference. And then how we can use this inference and this training in order to make something useful out of these machines. So this is how it sort of maps to the three different ways of viewing an LLM. We start from representing text in a machine-readable form in a useful way. We're going to look at how we can then build next token prediction machines using these primitives. And we're going to then see how we can turn these next token prediction machines into something more useful in order to enable sort of helpful and general purpose technologies, right? Okay. So again, a very fundamental question, what is a word, right? So when we want to process text in an automated way, we need to be able to define it as a finite set of what we call vocabulary items. The colors are sort of perceivable, right? Okay. So we create typically a vocabulary like that by observing on a corpus, for example, our training set, all possible tokens, and then we enumerate those tokens, and then we say, okay, so we encountered n tokens here, so these are our set of vocabulary items, so we can describe this corpus as a combination, sort of as a sequence of these vocabulary items. But then the question becomes, okay, so what is a token then? And you might be tempted to give an easy answer. Well, it's very simple. We just take everything and split it by a white space. So something like, I walked here turns into the two tokens I and walked. And it is, like, it worked well enough. It has been used for a long time. But we, once we start thinking about it a bit more in detail, we see that we run into quite some problems. So for example, what about this 2-hydroxybenzaldehyde? Is that one huge token? Well, probably not, right? We have definitely different sort of different subwords that comprise this token. This is from chemistry, and as you discover new materials, new proteins, you can stack them together pretty much infinitely. So creating a new token for each of those doesn't make a lot of sense. If you don't speak English as your first language, you might speak something like maybe Mandarin, which uses traditional sort of or simplified Chinese characters. You realize that they don't really use spaces, right? So what is that? Is that one token? Doesn't make sense, right? Then you have a sentence as a token. Is that each character is a token? Again, then you have a lot of tokens. Or my favorite 2025 word, which might tell you more than me if you use these words, right? So what do we do when we have a corpus? We have created our sort of tokenizer. We encountered all the tokens, and then we go ahead and we look at new words like the Lulu here. So how can we deal with these new words? It's an out of vocabulary problem, right? We don't really know how to represent it because it's a new token. We don't have it in our vocabulary, so we can't say anything about it. So as a summary here, we can split by white space, sure. It will create us meaningful units to a certain degree, but we will have a massive vocabulary of mostly rare tokens, and we will have this out of vocabulary problem, right, when we encounter new words. Well, okay, let's split by character then, right? Okay, we have a very small vocabulary, all the UTF characters, there are not that many, right? Most of them don't really appear, so we can prune them. But then we also have no out of vocabulary problem because you need characters to describe a new word as well, right? So we could just split this word here into the corresponding 6 characters. But a character by itself doesn't really mean anything, right? So we lose the meaning of the tokens. So what we actually do is we go a sensible middle ground where we have a data-driven approach for subword tokenization. So the way it works is one of the sort of algorithms that we're going to look at is byte pair encoding. But the underlying sort of intuition is that we learn the vocabulary from a corpus, very much like sort of inducing the tokens, but we don't enforce the rules of word boundary, right? So we can use language modeling, which we will talk about later as a way to do so. But what we will discuss now is the byte pair encoding algorithm, where we compose words from new words, compose new words from subwords. And when we learn them, we iteratively merge the subwords based on the co-occurrence. So this is the sort of the middle ground between we start by character, so we can represent everything, but we iteratively merge these characters into meaningful tokens based on their co-occurrence. So if we have tokens that co-occur often, we will merge them into a meaningful subunit. Which takes care of stuff like morphology, so prefixes and suffixes. In reality, we'll see an example later. So in principle, this allows us to take care of any kind of character combination that we might encounter in the future. In practice, of course, if this is a rare combination, then it is a rare combination of tokens as well. Whatever you use for it later might be not very useful. So the BPE algorithm, the byte pair encoding algorithm, works somewhat like this. It takes, again, as input a corpus and the number of sort of vocabulary items that you want to produce. And we start first by creating characters as the initial set of vocabulary. So we just take the corpus and split it by the characters that appear, so that it would be usually all the UTF characters that appear, or if you want to be a bit more simpler, all the ASCII characters. And from there on, you tokenize the corpus with these characters, and you repeat the loop here until you reach the final desired vocabulary size, so let's say 50,000. You find the most frequent pair of adjacent tokens in the text. You define them as TL and TR, and you merge them together to form a new token. So these two tokens that you have just merged form a new token. You push it to the vocabulary, so this is how this loop eventually ends, right? Because you increase the vocabulary. And then you replace all these occurrences of TL and TR with the new token, so that you actually have sort of represent this token, represent the corpus with this new token. So yeah, basically what I just said, right? You repeat this as long as the vocabulary is not big enough, and they just merge tokens that co-occur together the most. So if we have, for example, a very simple example, which will result in a horrible tokenizer, but for the sort of sake of visualization, it's good enough. If we have the corpus consisting of the three words low, lower, and lowest, we will have initial vocabulary of the characters, which consist of L, O, W, E, R, S, T, and the white space, which we obtain by just sort of getting all the characters in the vocabulary, right? So now we go ahead and count all the co-occurrences, and we soon see that L and O co-occurs 3 times, here, here, and here. The astute observer might also say, well, O and W also occurs 3 times, so we need to have some kind of tie break. I just go with the sort of the leftmost occurrence, right? So we go here, we take L and O, and we merge them into a new token LO, and then we replace the LO in the corpus. So now we don't look at each character, but rather LO is a single token, followed by W as the next token. Now we do the same process again. So we look at our corpus. We have the co-occurrence of LO and W, which again appears 3 times. If we had merged O and W first, it would be still the same sort of result here, but it would be merging L and OW. So it occurs 3 times, and we merge it together, LO and W, into a new token low, right? And here we sort of start to see in principle how this data-driven sort of co-occurrence-based approach takes care of some meaningful subunits. So low is a stem, right? So we have the stem of low, which represents something. Then we have the superlative and the comparative versions, so superlative being lowest and comparative lower. So it's just taking the stem and appending something to it. And we have the stem, which is sort of where most of the meaning of the word low comes from, is now a individual token. Now, if we had a bigger corpus, we would also have the sort of ER and EST as common suffixes. We would have them as their own tokens as well, but because our corpus is very small, we go ahead and merge somewhat weirdly low E, because this is sort of the next co-occurring, most co-occurring example, and we can do that until we run out of our vocabulary, right? So if we look now at how our tokenizer works after these 3 iterations, if we take lowest and we tokenize it based on our vocabulary, we take the low E, which is our longest token, right, following by S, which is a single token, and T is a single token. Again, it's not very good tokenization, but it's the result of sort of these few iterations. And more importantly, it also works with out of vocabulary words. So slowest is a word that didn't appear in our corpus, yet we're able to merge it into sort of tokenize it into a set of tokens, S, low E, S, and T. Again, not very good looking tokenization, but it works, right? Now, if we increase that to the size of all of Wikipedia or all of Project Gutenberg, then you can see how this will result in some more meaningful tokens with the example of sort of getting the low here, right? Right, so I hope this gives a good sort of answer to the question, what is a word for the context of language modeling, right? And language modeling is our core objective of what we're trying to do here. That is, once we have a way of dealing or going from a corpus to tokens or words, right, or subwords, we need some kind of way to make sense of these words, right? So over the years, the language modeling task has kind of been established, or has become the de facto standard way of doing so, and we will see a couple of reasons for why this is the case and how we got there. So language modeling is defined as predicting the probability of the next word token, so p of x at the time step n plus 1, given the sequence of previous words and tokens, so essentially the tokens x1 from the beginning until xn. So given all our previous tokens, what is the most likely next token? Or what is the probability distribution of all the tokens in the vocabulary to appear next, right? So the intuition, why is it a useful task? The intuition behind it is that if a model that can perform this task well, so if a model can perform this task well, it must have some kind of understanding. Understanding here is sort of loosely, hand-wavy defined, right? Machines process text, humans understand text maybe. So in order to sort of go from processing to understanding, to draw this analogy, we say this machine must somehow understand text, of course, whereas it's actually just representing and processing. But why do we say this? Well, consider the example below here, right? So I grew up in Germany, I speak fluent. What is the next word? For us, it's probably easy to guess. It should be German, right? And why is this such a powerful objective as well? Because it takes care of multiple things at once. So it takes care of syntax information. You can't say, I grew up in Germany, I speak fluent went. So you can't follow a verb by a verb. In this case, it doesn't make sense, right? It's not grammatical. Similarly, you couldn't just place any noun here. You couldn't say, I grew up in Germany, I speak fluent potato. It doesn't make sense, right? You don't speak potatoes. Similarly, if you say, I grew up in Germany, I speak fluent French, that's technically a correct sentence, but it's a bit weird, right? You would expect people coming from Germany to speak fluent German. So this takes care of essentially the syntactic, the semantic, and also some kind of world knowledge. So being able to solve this task demonstrates all three of these. And more importantly, which we will see later, this also gives us a sort of self-supervised signals. So self-supervision here means we don't need to sit down and create annotations. We just go and collect the data, and by just sort of creating blanks in the text, we can create data for us for free, right? So we can scale this up as long as we have data to access. So the simplest way to address this problem would be the n-gram language model, and we will see this at some point later today as well. So the way it works is we just count the co-occurrences of words as they co-occur in a corpus. So essentially, an n-gram model estimates the probability here of the next word given the previous n-1 words. So it would look something like this. If we want to get the probability of word at the position n, given the words at the position 1 to n-1, we just, overall the training corpus, we count the co-occurrences of the phrase or the sequence of tokens w1 to wn, and we divide it by the count of the co-occurrences of the phrase w1 to wn-1 without the token n, right? So that kind of makes sense. You just sort of count the co-occurrences, and then you divide it by how often the phrase co-occurs without the next token. So now a bigram example, where we just essentially use two words, would be approximated by just taking the previous word. So as an example, if we have the corpus, I like trains, I like to walk, I eat cakes, and I'm sleepy, the probability of I like, okay, this is wrong, I'll fix this as the probability of like given I, so this should be the other way around. The probability of like given I is about 50%, right? Because we have the transitions from I to like, eat, or am, and like appears twice, and the other ones appear only once, so you basically count 2, so I like, sorry here, 2 over 4, which is the total appearance of I. This gives you 50%, and for the other 2 you count the occurrence of eat, which appears once out of the 4 I's, and m, which also appears once out of the 4 I's, which gives you the 25%. So this should be a probability of like given I, right? So I hope that's clear. Now, of course, as simple as it is, there's also a lot of problems, and this is why no one's using it anymore, is you run into what sort of manifests itself yet again as a manifestation of the curse of dimensionality, right? So first you run into exponential counts, so a vocabulary of V words, let's say 50,000, and an n-gram language model means that you will need to perform V, or sort of the number of V to the power of n counts, right? Because you need to consider all possible combinations of the words. And of course, these counts don't really encode similarity. So you treat each token as an individual event. So I eat and I ate are completely different counts here, and they have no similarity despite meaning very similar things. And as a consequence, you will have a problem of sparsity where most of the n-grams that could appear because of this sort of exploding counts actually never appear in the training corpus. And then the model would assign 0 probability to them, even if they sort of create plausible sentences, and even if something similar has been actually encountered, right? So in order to circumvent this sparsity issues, we can make use of dense vectors, which learn sort of to represent the words with a much lower dimensionality, so much lower is the count, so something at the scale of maybe 300 other than 50,000 to the n of n-grams you want to count. So as a consequence, and if you create the training sort of in a smart way, you will get similar vectors for similar words. This is sort of, again, this goes way back into the 50s and is motivated by the distributional hypothesis, where you shall know, which says that you shall know a word by the company it keeps. So which means that words that appear in similar contexts should have similar meanings. So an example here, cat and dog both appear near, for example, pet, fur, and veterinarian, and both king and queen would appear somewhere closer to royal, throne, and crown. So therefore, cat is more similar to dog than cat is similar to king, right? Because they just appear in different contexts without knowing what, or without having a definition for what both cat and king means. So with these dense vectors, we can essentially address the problem of count-based representations, where due to the fact that they're sort of dense, they're compact and latent, and each of the dimensions represents more than just a word, or more than just a co-occurrence, or more than just a count. And similar words then lead to similar vectors in the vector space, so they're sort of geometrically similar, which we can make use when we process these vectors in a machine, so sort of with a machine, right, or with a computer. And this similarity then also leads to the main problem that we want to address with the main problem of the count-based representations. It leads to more meaningful representations of unobserved word co-occurrences. So even if you have never observed dog and pet, fur, and veterinarian in the training corpus, just because you have the vector for cat and dog, which are both similar, you can kind of infer, and you have observed that cat and pet is similar, you can kind of infer that dog and pet would also be somewhat similar, right? So one sort of foundational examples from some 13 years ago now is the word-to-vec algorithm to learn embeddings from context, and it works somewhat like this. So you start, your goal is to learn word representations by predicting exactly this similarity of context around a target word. So which means you have a data set of positive examples, which are given a word from its nearby context as you sample it from a corpus, and a negative random other word. In fact, it's actually a couple of negative random other words. Again, this is self-supervised. For a corpus, you can just go and collect these examples for free, right? You have a text, you can just take random words, take words from the context, and take random other words. The training task here is to just train a simple logistic regression classifier to distinguish between the positive case and the negative case. And because the input to the classifier, essentially, so this is the classifier here, this is the classifier, the input is just the embedding similarity as denoted by the sort of dot product of the word embedding. So you're trying to maximize the similarity of the words that are from the same context, while at the same time minimizing the similarity of the words that are sampled randomly, right? So as a consequence, what happens is that you're pushing, so for example, for the words apricot and jam that appear in the context, you're pushing the embeddings of both apricot and jam closer together in the vector space, whereas for random other sampling, such as matrix, Tolstoy, or zebra, you're actually moving them farther apart, because in order sort of to minimize this objective, you need to minimize this, and because this is a minuus, you basically need to maximize the distance here, so this needs to move to 1, whereas this needs to move to 0, right? So this means that these embeddings become more similar, and these embeddings become less similar. And because this is sort of a global optimization over a large data set, in the end, as a result, you will have words that appear in the similar context will get similar embedding vectors. So you could use either both C and W as embeddings, or you can just get rid of the C and just use the W. In the end, both these embeddings for both word and context encode this property. Okay? Now, for all that is good about the word embeddings, they assign a single fixed vector to each word, which is good because it already takes care sort of similarity, but words can have different meanings in different contexts, right? So if you think, for example, of polysemy, so the idea that a bank can encode multiple word senses, as we call them, so if it could be either a financial institution or a river bank, right? It's the same word, but means different things depending on where it appears. A similar apple could be a fruit or a company, right, that also deals with AI, among other things. Or more sort of other language phenomena, right, like coreference resolution. So if you say the trophy didn't fit in the suitcase because it was too big or too small, so depending if it was too big or if it was too small, it here refers to either the suitcase or the trophy, right? Just because, you know, if something doesn't fit into something, then one of those is either too big or the other one is too small, right? So if you have a fixed representation of it here, it doesn't really make a lot of sense, right? It can't encode both, or it does actually encode sort of an average of both, but when you actually use it, depending on what sentence you use it for, it can only have one meaning. It can't have both meanings, right? So this leads us to sort of looking for word representations that can change with context and so are therefore more expressive. So if we look at the example bank, right, and when we actually use the word bank, the vector for the word bank and the representation for the word bank should be different if you use it in the context of a river bank or if you use it in the context of a bank account. So one way to achieve that is to combine the embedding learning objective, like word2vec, which is for word2vec is separate, with the language modeling task. So, which leads us to neural language models. Technically, sort of the story is a bit backwards. Neural language models came before word embeddings, but they saw resurgence after word embeddings were widely popular, right? So neural language models are optimized to both embed token sequences and process the embedding sequence to build, therefore, contextual representations by predicting the next token from such contextual representations. So this is powerful because these embeddings are optimized not only to encode similarity, but also for the prediction task, right? And if you're trying to predict, for example, in the sentence here, the next word, whether it's being big or being small, therefore you need to learn the representation of the word it accordingly, whether the next correct word is big or whether it's small. So this essentially achieves exactly that, right? So each token's representation will incorporate the information from its context, which is then learned by predicting sort of the meaning or predicting the next tokens in the sentence, which then describe the whole sort of word in that context, right? Or describe the word in that whole context. So therefore, as we said before, depending on whether we have investment bank or river bank, because the word bank is also contextualized on the context, it will have a different representation based on whether we're using it in the context of river or whether we're using it in the context of investment. And still, unlike n-grams, these representations enable generalization of sort of, so we still encode the similarity of similar words that appear in similar contexts, so we don't have the sparsity issue like with n-gram language models, and instead we can generalize to sort of token co-occurrences that we have not encountered during training. So now, if we disregard fixed size context for now for a bit, the question is then how can we use the context in order to model to model this language modeling task. And if we don't use the fixed size context where we have whatever 5 tokens that we just use as an input, one way that we can do is to use the bag of words representation, where we just sort of take the embeddings of all the words here, x1, x2, x3, and we just average them out. But the problem is that this sort of loses the word order, right? So if you want to represent dog bites man and man bites dog, in this way we would have the same kind of representation for the same sentence, but again, word order kind of makes a difference here, right? So whether dog bites man or man bites dog, these are two different sentences. So one of the solutions is here to modify the network architectures that we can use. So we have model architectures that explicitly model the previous state in a sort of process sequences in a temporary fashion, right, or in temporal fashion, and this is the recurrent neural network, where we essentially, when we calculate the representation of a token or a state, we make use of the representation of the previous state explicitly, right? So this is in its simplest form, is how an RNN is defined. So we just sort of add the representation of the previous hidden vector multiplied by a set of learnable weights, and we add it to the new, the current representation, which is multiplied again by another set of weights here, right? So there's, again, this is very, very oversimplified. There are some architectures that deal with this in a more sort of advanced manner, like LSTM and GRU. So there's sort of more vectors that take care of the context and the previous states, but the idea generally is the same. You sort of, in order to get the representation of the next token, you need to calculate the representation of the current token, and this way you model the previous context for the task of representing the current context. It looks somewhat like this, right? You calculate, if you say you have the sentence I like trains, you calculate first the representation of I, you make use of that to calculate the representation of like, which you then use to calculate the representation of trains. So trains here is sort of inoculated, is aware of both the hidden representation of like as well as the hidden representation of I, right? One example of this, this is slightly more recent, from 2019, is the or 2018, is the Elmo language model, which essentially is a language model that uses a advanced form of RNNs, so LSTM, in order to solve in order to model the language modeling task. So what Elmo does here is minimizing the cross entropy loss of predicted next token versus the ground truth. So this is the objective here, and if you're a bit confused by what this here means, is basically just the sort of cross entropy between the distribution of y and the correct token, because there's only one correct token. So it's essentially a distribution versus a one hot vector combination. I use this sort of to write it a bit more shorter, right? And both the sort of the distribution is being obtained from both a forward pass, so we take we take the previous context, which of the words here, which we obtain by using an LSTM to encode all the previous tokens, and they also use, so because it's a by the LSTM, they also use the backwards pass, so they use all the future tokens to encode the representation of in a sort of backward LSTM, which processes the sequence backwards, right? And then they just use both of these to predict essentially the current token, and then the loss for both of these is summarized and then minimized, right? So here the RNNs process the, or the LSTMs process the sequences before and after the token trying to be predicted. And we're using a essentially feed-forward neural network to map their hidden representation back to the vocabulary space, and then softmax that to get a probability distribution, and then we calculate the loss based on that probability distribution. So one of the things maybe that is worth pointing out here is teacher forcing, because that will appear again. Teacher forcing means that rather than sort of autoregressively generating a token and using that to predict the next token, during training we always use the ground truth previous context to model the next one, so that we don't sort of digress immediately. So this helps with training and it's also faster. Now, why are we not using RNNs anymore to build large language models? It's mainly because they are trained with backpropagation through time, and because you need sort of the previous representations in order to calculate the next representation, even during training, right? So backpropagation through time sounds fancy, but basically what it means is we need to unroll the computational graph to a standard backpropagation graph in order to obtain sort of the final representation Tn, which is for long sequences very slow and not very efficient, right? And even though we can do all that and we can train the model this way, right? Long-range dependencies are still hard to process and to model, even with these advanced LSTM and GRU architectures. And all of that is because the past context is encoded in a single vector, or in the case of LSTM, GRU in multiple vectors, but still it's still compressed into a single or a set of a few vectors, right? So this is an information bottleneck. And this is essentially what motivates the transformer architecture, which goes back to the fixed context window approach, because as the transformer was proposed, the GPUs that can fit these models were getting bigger and bigger, so we can encode bigger and bigger context windows. And this way we have access to the past information directly, not sort of through a sequence of calculations of previous steps. So transformers model sequence at the token level, and unlike RNNs, they have access to representations of all previous and potentially future tokens, here abbreviated as TJ, right? And different from RNNs, they're doing that with the attention mechanism, which we're going to look over briefly. Intuitively, attention basically represents the relevance of a collection of vectors or items, such as embeddings, for example, with respect to another vector or item. Right. So in the case of self-attention, we don't attend to anything sort of other than the sequence itself. So it means we calculate for each element in the sequence xi the relevance to all the other elements in the same sequence xj. So this is essentially a very simple definition of the attention, right? The attention weight between I and j is the softmax between xi multiplied times xj. So this gives us a score. Right, so for each x, we will get a kind of distribution over all the other items in the sequence, and then we sum them all up, multiplying them again with the item itself, in order to get the hidden representation of the attention output. Right, so this looks somewhat like this. We have, again, if we have the I like trains example, if we apply self-attention, the hidden representation of each of the tokens here, like H3, for example, for trains, is being attended to or has attended to both I and like. Similarly, for H2, it has attended to trains and I. So each token's hidden representation is represented essentially as a weighted relevance sum of all the other tokens in the sequence. Now, looking at this formulation of attention here, we see that the embedding X fulfills actually three different roles, right? One is being the unit for which the relevance is measured. The other one is the unit of which the relevance is measured, and then the actual value of the embedding that is then being multiplied with, right? So it makes sense to separate these functions by using distinct weights. So here we see that xi is, and you might not see that because of the colors, or maybe it's me who doesn't see the colors very well here. But so xi here is essentially the query, xj is the key function, and xj in the final calculation here, when the attention weights are being multiplied back to the embedding, is the value, right? So we can, why not? We can create three different embedding matrices, which we then use to project to the original embedding into these distinct functions to make sure that they sort of learn these distinct roles. Again, with learnable parameters, wq, wk, and wv. And then when we calculate the self-attention between xi and xj, the way it looks like is somewhat like this. So xi and xj are two vectors, which we then sort of project into their corresponding query key and value embeddings. We then take the query of I and multiply it with the key of j. We softmax it in order to get a sort of part of the probability distribution, and then we multiply it with the value of j in order to get the actual hidden representation. And we do that for j, and we do that for all the elements in the sequence. In the end, we sum it up to obtain the final hidden representation of the vector I, right? Sorry, this isn't the hidden representation, here is the attention weight. Then we, again, if you're wondering why we're dividing it by the dimension of the dimensionality of Q, is again stabilizes training. But all this sort of you might have already heard. But what's more important here for the text processing part is that nowhere do we need to access or calculate the previous sort of set of weights before we, like n minus 1 or t minus 1 when we calculate n or t, right? So all this can be done in parallel, and all this is done in parallel. So we can parallelize this calculation by using matrices instead of the vectors. And this is what allows us to calculate sort of the representation of a sequence in parallel, which allows it to perform faster and scale with the growing compute, right, which scales according to Moore's law. So the more compute we have, the more sort of bigger matrices can be multiplied. This means we can calculate bigger attentions, right? We can increase the dimensionality. And this is something that contributes to the scale of this whole endeavor. And this is why, in the end, transformers are winning over all the other architectures that we've seen before, just because they scale much better with the amount of compute that is becoming increasingly bigger. So we take this sort of attention calculation and we do some more deep learning tricks. So we can match the dimensionality of the embeddings and the hidden dimensions in order to stack them, just as we can stack RNNs, so that we can perform the same calculation multiple times over and over. We use layer norm and sort of a feed-forward neural network and residual connections. So residual connections usually give access to higher layers in order to access representation from lower layers. So if your layer sort of isn't learning something that is supposed to, it can still do a short circuit in order to access the previous representations. In the original transformer paper, they just used a simple sum to add up both the embedding before sort of the self-attention and before the feed-forward and after. The layer norm is a normalization sort of trick which normalizes all values across the input, which is kind of similar to feature normalizations here. So we take the feature-wise mean of x and feature-wise standard deviation of x, and then we normalize. And this is sort of how the whole transformer stack looks like. We start with the embedding, we do the self-attention, we add the embeddings back again, we normalize it, we feed it through a feed-forward neural network again, we add the pre-feed-forward neural network here, we do another layer norm, and we get the hidden representation. And we can stack this again and again and again. And I think one of the things that is worth pointing out is that this is sort of, all of these operations preserve the position-wise, even though they're being performed in parallel, they preserve the position-wise representation. So x1, it's still, or the hidden representation of h1 still corresponds to the embedding of x1 and sort of the token that x1 represents in the end. So the feed-forward neural network here is position-wise to make sure that we don't sort of screw up the position and the order of tokens. And again, we can do that sort of multiple times in parallel, right? So the motivation behind it is that there are different types of the relationships between words, such as semantic or syntactic. So for example, coreference is a semantic one, whereas syntactic is something like, grammar stuff, like head independent. And, we can use multiple self-attention heads which model or which learn to model these different semantics and syntactic relationships separately. We then need to project it back again into the original output space in order to be able to stack them, but this is just a sort of a projection layer. And one final thing that is worth pointing out, which is again more relevant for sort of sequence processing and specifically text processing, is we have a context-based, sort of fixed context-based approach. We have weighted sum of the inputs, but sum is commutative. So if we just do that, the representation of dog bites man and man bites dog in the end is going to be the same, right? Because there is no way of modeling order in our transformer as we have it now. So the solution here is to use positional embeddings in addition to the word embeddings, and addition here is taken by word. You just add them together. And then this way, while the embeddings sort of themselves represent just the word, the positional embeddings represent just the position. So if you add them up, you have word plus position. In the original attention paper or transformers paper, what they used is cosine and sine functions, which then looks somewhat like this. So as you go up in time and as you go through the dimensions of the embedding here, they create sort of these waves. So each time step at each dimension will have a slightly different representation, which then sort of encodes time. But there are more advanced techniques there, some which essentially learn relative embedding distances up to a certain distance, some that modify the queries and keys. Ask me later, I can point you to the papers if you're interested. But this is sort of the idea, right? So we use something that is that does encode the distance or the position in the sentence in order to make sure that we don't lose this word order. Right, so one example of that, and this is essentially pretty much the modern LLM architecture without all the sort of bells and whistles, is the causal or forward or left to right or decoder-only language model, such as GPT-2 or Llama, is again is using the transformer architecture to perform the language modeling objective of given the n previous tokens, let's calculate n minus 1 previous tokens, let's calculate the probability of the nth token, right? So again, the final output here, we use the transformer, we stack them, and then we take the final hidden representation, we project it back into the sort of vocabulary space, essentially an unembedding operation. So, we use the same embedding matrix that we use to embed the inputs, just transpose it. So the embedding matrix at the input takes a sort of one-hot vector representing an index and maps it into a hidden representation. Here we take a hidden representation and map it back into a distribution over the vocabulary indices. So this is achieved with softmax, and then we again do the cross-entropy loss, so minimizing that again with teacher forcing with respect to ground truth tokens. So the way it looks like is somewhat like this. If we have the sentence "I speak fluent German," right? In order to calculate at each step the representation of the or sort of the probability distribution of the next token, let's take the third step and the fourth token as an example. We have the loss here, which is our cross entropy loss. So over all the sequence, we're trying to minimize the cross entropy between the prediction and the actual token as an index in the vocabulary. And we do that by essentially softmaxing the hidden representation of the previous token, unembedded using the transposed embedding matrix, which maps from the sort of this being the, what did I say, being the sort of hidden representation back to a distribution of the token indices. Now, if we look at it like that, this all makes sense, but again, maybe someone might point out, well, but the transformer sort of represents, in its hidden representation, already represents all the previous, the current, and the future tokens due to the self-attention formulation, right? We calculated across the whole sequence. So now that's a problem, but only a small one, because when we actually implement this, we mask out the upper triangular matrix of the QK calculation. So when we calculate the representation of each token, the future states are then consecutively being masked out. So if we look at, for example, our example here, right? We have 3 tokens which we represent, and we want to learn the 4th token. We mask out the representation of the 4th token, and because we softmax this, and softmax over minus infinity, essentially yields in a 0 score after the calculation here. So the distribution of the attention is only concentrated over the first 3 tokens, which is what we want to achieve, right? Because otherwise it would just learn the shortcuts between the input to the output. So this way we actually make sure that we only attend to the previous tokens, here, hence the name causal or forward or left to right or decoder-only language model. So we're only using the previous tokens to model the next token. Right, so this basically is the basic recipe for the LLM architecture. And what we're going to do now is we're going to look at how we can use these ingredients to perform language modeling at scale. So we're going to look at the first L here in LLM, right? So what makes a language model large? And we will, again, revisit that in the second part of the lecture with Vijay. So what makes the language model large is scale, and there are three ingredients which contribute to that. One is the architecture. So with the transformer decoder, we can, as I mentioned before, we can stack these transformer layers. There are some difference in details, like positional embeddings. Some activation functions are different, but in the sort of the core idea is still the same. We just take the transformer block with some more modifications, and we stack it to make the model bigger. The other thing that we can scale is the number of sort of the size of the training set that we're using to train the model. Right? This typically consists of web crawls, books, academic papers, Wikipedia, code, and other things which are maybe not very legal to use, which is why we hear some, sort of, what is it, lawsuits coming up. So it's an interesting thing to follow as well, where this will go. And of course, compute. So as we sort of mentioned, Transformer is very effective at being able to scale with the existing compute. Compute sort of scales by itself, and now more and more so compute is being scaled specifically for LLM development. So as we scale the compute, we can train and fit bigger models. So we can fit bigger models, we can train it on more data, we can train it faster, for longer, more efficiently. And this altogether essentially gives or results in the situation where we're today, where we have these large models which perform all sorts of useful tasks. So when we look at the pre-training objective, as I mentioned, LLMs are trained on a diverse corpus of different sort of different sort of domains, such as web crawls, code repos, scientific papers. I hope you can read this here. This is, for example, the DOLMA open source training corpus for training open source LLMs, and this consists of the common crawl, GitHub, Reddit. So here are different sort of domains of the data. There's scholarly papers, there's code, there's popular literature, there's sort of encyclopedic knowledge. And yeah, the more you use of those, if you're allowed to, the bigger your training corpus becomes, the more diversity and the more sort of data you get to train your model on. Here, quality matters also as much as quantity, of course. So here's an example of how when we use, I hope that's the correct, when we use filtering, we can remove some low quality and duplicated content, and this in turn increases the performance. So here's an example from this paper again, where they show that different filtering techniques over the baseline improve sort of the model performance in downstream tasks. So here specifically is a sort of multiple choice data set, or a common sense multiple choice data set, and we can see that if we remove some hate speech and NSFW words, this then can improve the performance of the trained model. Similarly, if we remove nonsensical texts, one of the rules, for example, is to identify how many commas and points and punctuation is there per sentence, and if it exceeds a certain threshold, then probably the sentence is nonsensical, so we remove it. And there's basically a bunch of these rules. So as we use more of these rules to clean and deduplicate and filter the corpus, again, the downstream performance of the trained model on some sort of useful and real downstream tasks improves. And the training mechanics, as I mentioned, so there's not much different from what I've discussed before, bar some sort of exceptions which we didn't cover. So we do the weight tying, the cross-entropy loss, the teacher forcing. And one of the things that we do is we just sort of take all the data, we divide it up into the context window that the model can process, and we just pack them into single chunks in order to be more efficient with the data that we process. So we don't have to use padding tokens, which essentially don't teach us anything. One thing, and we will again cover this in a bit more detail later in a second lecture, is that performance of these models improves predictably with scale. And scale, we can scale, as I mentioned, all three things: data, compute, and model size. So the loss on the test set of this model, so essentially the cross-entropy loss, decreases as a power law with more compute, data, and parameters. So here we can see that as we use more data, bigger models can make more use of that, whereas smaller models at some point overfit here. So the loss goes back up again as we use more parameters here to the right. And here we see that as we use, as we use longer training, so these are sort of the yellow, or from blue to yellow, this increases the training budget. As we use more parameters, models can use more training without overfitting, whereas smaller models, again here as the loss goes up, start to overfit after too much training. And then there's also, again, more about that later. Some abilities seem to emerge or drastically improve at scale, such as few-shot learning or chain of thought reasoning, instruction following, though, again, emergence is a hot topic, but there's also an argument that emergence is not actually a model property, but rather a metric property that is used to measure that specific emergent behavior, but we can discuss that maybe at some point later. I can point you to the paper as well. So now we know how to train this model. We have trained it, right? So the model learns to predict the next token, given all the previous tokens. But at inference time, we actually need to generate text from this estimated probability distribution, right? So how do we do that? And here's a very simple loop of how we can generate tokens. So we take a trained model, we take the prompt that we want to continue, we take the max tokens that we want to generate, and we tokenize our prompt, we give it to the model, and while we haven't reached the max number of tokens, we just sample from the model the probabilities of the next token. We select the next token, we append the next token, and we repeat that until we either encounter a special token that denotes, okay, stop, this is the end of the sentence, or we run out of tokens because we reach the max tokens, and then we just convert it back to a string. But the question is now, so how can we implement select probabilities? Because depending on how we implement this, so how we can actually select a token from the distribution affects the final outputs, right? So the simplest way is just to argmax. We have a probability distribution. We take the maximum probability and take the corresponding token. But the problem is that this can be quite repetitive and deterministic, right? So we can get repetitions, and just because sort of the next token is the most probable one, we always pick it, and then we can run into this kind of loops that you might have encountered, the cat set on the mat, and so on and so on and so on. Now we can go to the other sort of extreme, and we can randomly sample according to the distribution that was predicted. That is more diverse, but it's also more risky, because if we randomly pick a very low probability sort of a low probability token, then first of all, it doesn't make a lot of sense, but also because we added then to the context, the model then needs to predict the probability of a sequence that it has not really encountered before, and doesn't make a lot of sense, right? So this can lead to incoherence, because we include low probability or nonsense tokens. Now, what is more useful is, for example, using temperature scaling, which controls sort of how sharp the distribution is. So between the head and the tail, how much weight do we give to the head of the distribution versus the tail, right? So the sharper the distribution it is, the more we go towards greedy decoding, where we sample more so sort of more probable tokens, whereas if we scale the temperature up, the distribution gets flatter, so which means that the less probable tokens become relatively more probable, and then we get more sort of diversity, but also we run more into the problem that we had with the random sampling, right? And then there's other things that we can combine it with. So for example, top k sampling, where we can sample the top k tokens. So we say, okay, we're going to only use the top whatever 40, 50, 100,000 tokens, and the rest we just set to 0. Or we can say top p, where rather than saying we're going to use n tokens, we're going to use only tokens that add up cumulatively to a certain probability mass, right? So if we say we only want to sample from the top 70%, we then mask out the last 30%, and we can combine that again with the temperature to sort of see which part, or how much we want to include into this probability mass and not. And that's essentially how you would sample from a language model as you encounter it from the, let's say, OpenAI API. So you know these parameters if you've ever used OpenAI API. Now it is worth noting that we can actually enforce arbitrarily complex constraints on this next token generation, right? Because it's just select something from probability distribution. So the idea is that at each decoding step we can adjust the token probability down to 0 according to some defined rules, and the rules can be sort of from very simple to increasingly complex. For example, we could implement a repetition penalty where we decrease the probability of tokens that we have already encountered in the text. We can blacklist words, such as, for example, a swear word filter, right? where we make sure that certain expressions don't appear. We can even go a bit more fancy than that. We can match the outputs according to a CFG or a regex. So for example, if we want the LLM to output an email or a sort of JSON compliant output, we can enforce that as well. Or we can make it validate against a Pydantic or JSON schema in order to sort of take the output and plug it directly into code, if you're daring enough, right? So there are libraries that are handle this already. The point is you don't have to implement that from scratch. There's outlines, guidance, and they're also implemented in the modern inference frameworks. So this allows us essentially to create structured outputs from APIs, which are then, so you use something, you use an LLM to process a piece of text, and then you get a structured output. You can plug it directly for further processing in the code, so you save yourself a bunch of error handling and parsing of these outputs to get the proper output. It is worth saying, though, that if you haven't actually trained the model to do this kind of output, you just mess with the probabilities. Again, you get some tokens into the context which are low probability, and then you might get some weird outputs. Which leads us to sort of the core point. Well, these models are quite impressive in that they can predict next tokens, and with scale this ability increases even further, but it's not particularly useful to just predict the next token. So they're good at continuing text, but it's not actually what we want to achieve from an assistant, right? So to visualize this, we have on the left-hand side, this is what the model was trying to do. So France is a capital, blah, blah, blah. Its capital is a largest city and main cultural economic center is, and the model will probably generate Paris with quite sort of high confidence, but it's not very useful, right? What we would actually want to do is we want to be able to ask the model, so what's the capital of France? And then it would generate the answer, well, the capital of France is Paris. So we want to go from the left-hand side to the right-hand side, right? So we need to enhance the model from this text predictor to the helpful assistant on the right-hand side. And this is exactly the goal of instruction tuning, where we take this sort of general language knowledge that we have acquired during pre-training of this massive corpus for a long time, and then we adapt it to some specific behaviors through additional training stages. Right? So this is a bit of a misnomer here. It's called instruction tuning, but it's abbreviated with SFT. So it is because it's supervised instruction tuning, so you're doing supervised training, but you're not sort of supervised training as any kind of training, and supervised fine-tuning is any kind of training of any kind of supervised training of an LLM, right? Here specifically we're doing instruction tuning, which uses still the same objective and performs sort of just continuous training, but what we change is the data format. So instead of having essentially the next token for formulation of the task, where we just have the packed sentence and we try to predict each next token, we format data specifically in an instruction and response pair. And the data we sample from a curated set of large sort of existing NLP tasks and data sets, and luckily it's 2025 or 2026. The last 10 years, all people have been doing is creating more of these benchmarks, more of these data sets. So there's thousands of NLP data sets for summarization, question answering, translation, natural language inference, and so on and so on and so on, which we can draw upon in order to create this large, diverse instruction tuning data set. Right? Again, nothing about the model architecture or the training objective changes. We still do the next token prediction. We just format the data differently. So if we then evaluate this model that is trained on a collection of such tasks, we want to evaluate it with respect to the ability to generalize from what it has seen in terms of instruction and expected outputs to unseen types of instructions. So we're evaluating it on unseen task types with accordance to their task-specific metrics. So for example, if we train on a collection of question answering and summarization, we would then evaluate it on the translation task, and the translation task will have its own blue and rouge metrics, which we then would establish the performance of the model by looking at specifically these metrics. So the way it looks like is somewhat like this, right? You have the instruction, you are a helpful text assistant, and then you have a request, can you capitalize the word cake? And you get the response, well, here's a capitalized version of the word cake, cake capitalized, and you take this as a training instance in order to run the next token prediction objective on top of that. How that exactly works we'll see in the next slide. But basically, the intuition is that if a model that can perform well under such evaluations, so we would then evaluate whether the cake is actually capitalized, right, is said to perform any natural language task. And any here is, again, in quotations, because we can only say how well it performs on the stuff that we evaluate. But the point is that we take the knowledge of a task that for a supervised fine-tuned model is technically encoded in its parameters, and we shift it from the parameters of the model into the ability of interpreting it from the text instructions. So what we're doing here is we're not training a model that can capitalize words. We're training a model that can read, again, or process the request and act accordingly, right? And if we change the request is just normal human language. If we change the request to some other request, so instead of whatever capitalize, we say translate or make it sound like I'm a pirate, then the assumption is that if under these evaluations the model performs well, it can perform this kind of task. And this is how we essentially get to this more or less general language processing sort of NLP machines, right? We train on a big collection of tasks, we evaluate on a unseen task, and we observe that the performance of the model is still reasonably high. So in practice, this works with so-called chat templates. So conversations such as instructions and the corresponding outputs are formatted with special tokens in order to sort of represent the structure of the conversation, and these tokens are then, or their representations are learned to represent roles, turns, and so on. So for example, if we take the previous instruction here, you're a helpful text assistant, and can you capitalize the word cake, and we turn it into a chat template, we have these special tokens here, such as the begin of text, which just sort of says, okay, here we start. Then the header tokens, which say, okay, this is sort of a system message, which this is something specific for the Llama model. It just says today is this day, right? And you were trained until that day. And you are actually, so this is the part where we add the instruction or the system message, right? You're a helpful text assistant. We then format the request as a user turn, and then we would expect the LLM to autocomplete starting from here. It's sort of assistant turn, which is here's a capitalized version of the word cake, right? So this helps us, or this helps the model in first, when we train it, to recognize and learn turn structure, so that when you have an instruction, this is typically followed by a response, right? If we have a user turn, it is usually followed by an assistant turn, and so on. And it also helps us to sort of make sense of the tokens that the LLM outputs. For example, we have the EOT ID, which indicates that the turn is done. So the model predicts that the answer is completed when it generates this token, so we can stop sampling it, and then we can just take this output, detokenize it, and give it back to the user. Right. So I hope this makes sense, because in the last 10 or so minutes, we're going to go beyond that, right? So we have now a sort of general purpose machine that can follow instructions, right? But there might still be some problems. So there are some harmful outputs. An LLM can, even if we filter and remove all the sort of harmful inputs, it can still come up with harmful outputs, right? It can suggest it to follow something dangerous, produce toxic content, or it can just give, more often than not, some unhelpful responses. If you want to see unhelpful responses, we're going to have some examples later, but you can certainly imagine some by yourself, right? So the problem is because when we do this, we teach the model what to say, but not necessarily what's better, right? So like some tasks, they might have multiple right answers according to the metric or according to the sort of next token prediction, right? But some of them might be more preferable to you and me and everyone here rather than others, or most people rather than others, right? And these preferences might be either implicit, so you can't really say why you like one more than the other, or they might be even subjective, they might be different for 90% of the people, right? And these are hard to model with the next token objective. The solution here is to learn these subjective and implicit signals from human judgments of LLM-generated outputs, and not just from sort of the NLP tasks that we use in order to instruction-tune the models. So instead of asking humans, again, going away from demonstrations, instead of asking humans to write perfect responses, what we do is we ask them to compare the model outputs. So we ask an LLM to generate 2 or more candidate responses, or we can even use multiple LLMs to generate the answers, right? We then take this data, we go to a human annotator, and we say, okay, well, choose and rank which one is better, right? So if it's binary, just pick a winner. If it's a list, then rank them. And then we collect these triples of prompt, winner, and loser, or if it's a list, we collect a sort of prompt and then the ranked list of the answers. So here's an example of a unhelpful answer. So if we ask the LLM what is malaria, it might give a whatever CDC or WHO definition, right? Or it might say malaria is a disease. Well, thanks. I would have probably guessed that myself, right? So then you go ahead and say, well, I liked response A better than response B, and then our data set will become prompt what is malaria, the winner, which is A, and the loser, which is B, right? We can ask multiple people, so we just don't get only binary, but sort of probabilistic guesses of which one is better and which one is worse. We can ask multiple people for multiple options, so we can create ranked lists, and so on. But the idea is that we use sort of this approach because these comparisons are generally faster to collect, right? You don't have to write a whole answer, just say A or B, so left or right, right? And you don't need to think about it for too long. And they also capture implicit sort of differences better, right? You don't necessarily know what is better, but you don't know what's the best, but you know that one's better than the other. Or if you would have written it, you would have written it completely differently. But from those two, you can still say which you like more. And the way you collect this is either explicitly. So a lot of if you know platforms like Turing and so on, they ask basically you to annotate a lot of LLM data, right? Paying you what's dimes on the dollar that then they use to sell it to companies like OpenAI. Or you can also, if you own a platform like OpenAI, right, or ChatGPT specifically, or Claude, you can use the implicit signals such as the upvotes of the users or regeneration requests to reason about whether or not an answer was preferred or not. Right, with this data, we can then go ahead and do the following thing, and it becomes clear why we're doing that. So we can train a reward model to predict the human judgments of LLM responses. So essentially, we train a model that, given a prompt and a response option, to assign a score to that response option. And essentially, when we have this data set of the triplets, right, prompt, winning, and losing response, we train, once again, this reward model such that, again, we don't know the exact scores. All we know that the winning prompt should be scored higher than the losing prompt. So this then translates into the training objective of where we minimize, again, because this is minus, so in the end we maximize this difference, right? So the higher the winning prompt scores over the losing prompt, the better. So this, as a consequence, this pushes the model to assign higher scores to those preferred responses, right, and lower scores to unpreferred responses. So often we can take the fine-tuned model, then we can replace the language modeling head with a regression head. So rather than predicting the next token from the probability distribution, we just sort of predict a scalar, right? We concatenate the prompt and the response as an input, and then we just predict the score as output, training it with this objective here. And then we train it on the collected preference data. And this then, in principle, if this model performs well, this gives us a model that can score any prompt and response pair according to the learned human preferences, as long as it's not too far away from what we have trained it on, right? So one example of how we can make use of that is the reinforcement learning from human feedback via essentially proximal policy optimization. So we have this reward model. We can use it to improve the language model, right? We can maximize the following objective using training the model to generate responses that have the maximum reward subject to not deviating too far away from the original model. Now this term, term here means that we penalize model updates that move the model too far away from its original form. And the reason for that is because, well, this is also a trained model, right? So it has its own biases, it has its own blind spot. It might mark something as very high that doesn't look like language to us, right? So in order to make sure that this doesn't happen and the model trained here basically doesn't learn to hack the weaknesses of the reward model, we make sure that it doesn't deviate too far from what we perceive as normal language as scored by the sort of the original model, right? Now this is a objective that is maximized with proximal policy optimization, which is a standard reinforcement learning algorithm, and you will learn about reinforcement learning, I think, tomorrow, so I won't go too much into detail here. Just for the framing, the policy that we're speaking about, that we want to optimize is the LLM. The action of the LLM is to generate a token. The state with respect to which the action is taken is the previous prompt plus all the generated tokens so far. And of course, the reward is, after you generated the full sequence, is the reward from the reward model for the full response. So PPO is sort of as a brief overview, updates the policies of the LLM based on the final reward that we get from the reward model, assigning credit back to the individual token level actions that contributed to the outcome. So as a consequence, updating the weights to increase the probability of token choices that contributed more to the high reward output and minimizing those which yielded sort of low reward output. So we need, I'm going to say something which I'm going to completely backtrack on in the next slide, but we need reinforcement learning for this formulation because we have the token generation step in between, right? So token generation, we've seen a bunch of code, is a non-differentiable step. So we cannot sort of just backpropagate the final reward all the way to the inputs. We need to have something that deals with non-differentiable inputs such as reinforcement learning. And how that works, you'll hear in the reinforcement learning lecture. But now let me walk back on exactly what I've just said before. Turns out you don't need reinforcement learning to optimize sort of human preferences. You can decompose the perfect policy that you would learn here into a direct supervised objective under the direct preference optimization. So the objective specifically looks like this. What it does is we increase the probability of the preferred response, decreasing the probability of the dispreferred response here, right? So again, we similar to the reward model that we have trained before, we directly incorporate that into the loss, right? And we normalize it to the reference model again, so it doesn't deviate too much from what we perceive as actual language. So in the end, we're not actually increasing the probability, but rather the ratio of probabilities of trained versus the reference model. So increasing the winning option, decreasing the losing option, right? So the advantages over full reinforcement learning is that there's no reward model to train, so we have one model to train instead of two. There's no reinforcement learning optimization loop. Reinforcement learning is a pain to train and to get correct. So if you just do supervised learning, it's much faster, it's much easier, there's less things that you can do wrong. It's more stable, easier to tune. It's also computationally cheaper because for the reinforcement learning, we need to actually generate token by token the full answer until we get the reward score so that we can then use the PPO to assign credit and do the policy update. Whereas here, this is supervised learning, so we don't need to generate. We can go again sort of to the next token prediction, but using over the whole sequence, right, with teacher forcing, but using this loss formulation. But we do lose the full flexibility of reinforcement learning, which, because we don't really generate any new sequences, we can only train on the preference data directly, which again is not really a disadvantage because the reward model was trained on that data as well. So even if you use reinforcement learning to generate completely new sequences, whatever you get of human preferences or the human preference signal is still just trained on the data that you're training the PO on, right? So the ability to incorporate other reward signals is probably another one that we need to mention. So for example, if you wanted to incorporate penalties for brevity, you need to do it in this loss objective directly, not sort of via reinforcement learning. One thing, again, which we will maybe cover a bit later is we can also look at reinforcement learning from verifiable rewards. So unlike from human feedback, which models sort of implicit and very subjective things, verifiable rewards are very objective and very explicit, and we can verify them formally, for example, by running a program, right? And examples include we can sort of ask a math question and then see whether the output is the correct answer. We can run code. So we can write code and then run test cases against that code to see whether they pass or not. Or, and this is going more towards sort of the agentic stuff, we can look at an interactive environment where we have a sequence of steps which solves a problem, like, for example, whatever, go somewhere and open a door, and then the environment will give the signal that the door has been opened, which you can use as a verifiable reward. So this goes more also into the traditional reinforcement learning. And the advantages here is that, again, we don't need a learned reward model because we can use the actual correctness as reward as a signal from the environment wherever we're using that, right? So if it's code, then if all the test cases pass, then this is our correctness signal. And in principle, especially with sort of dynamic environments, we can potentially create unlimited reward signals because we can generate infinite problems. So if the task is to navigate via text in a room, we can just generate random room layouts, right? Or if the problem is a math problem, we can use a generator to generate similar but different math problems in order to train the model on them infinitely, right? If we wanted to. So this can be useful if many valid solutions exist. For example, if you write code, you can write 5 different ways the same piece of code that has the same semantics. It doesn't matter what you write in principle as long as the execution is correct, right? So here it doesn't matter how you get to the point as long as your final solution is correct. So I think wrapping up our lecture, let's just have a look at what we have talked about, right? So there's, as I mentioned, there's 3 stages for LLM training. And the summary is we have some pre-training data. We use the next token prediction objective to train a large transformer model to obtain a pre-trained LLM, which is our, so to speak, autocomplete machine. We then take diverse instruction data, which consists of instruction and response pairs of different NLP tasks, such as here sentiment analysis, summarization, translation. And we continue the next token prediction objective on specifically formatted instruction data in order to obtain an instruction-tuned LLM, which is then, as I mentioned, a generalist NLP task solver. Finally, we then collect preference data, which consists of prompt and the corresponding responses and their scores, or maybe sort of rankings of winning and losing responses from humans or from some sort of environment, or both. And we perform preference alignment using reinforcement learning or the supervised version of it, where we have the algorithms that we discussed before. There's a bunch of them. That's why I'm saying ETCPO. There's like, you know, each one coming out, a new one coming out each month, which then leads us with an aligned LLM, which is a helpful assistant, which is what you can download from Hugging Face, which is what you can prompt sort of in the OpenAI or VLLM sort of providers as a model to get outputs, right? So a quick shout out, I don't think we have enough time to cover this, but there are things that make LLMs expensive. That is the training, inference, and fine-tuning, right? So we have, we need to train it for a long time. Inference, as I mentioned, takes a long time because we need to generate pieces of code. We need to sort of run pieces of code that generate token one by one, right? Which takes a while, and then it also requires a lot of memory. And then when we fine-tune, we need to again load the whole model into memory, which requires a lot of memory as well. So there are optimization targets across all of these: memory, compute, and parameters. And just as a brief thing, you will have the slides later, access to the slides later. I think you can look through them. So one is the optimization of inference. When we calculate the representation of the or when we calculate the next token representations for the prediction, we essentially reuse the key and the value vectors from previous turns, right? So when we calculate for step Q3, we'll need to calculate x1, x2, and x3, and also v1, v2, and v3. So if we have to then calculate for the token 4, we still need to calculate Q4 and K4, and this matrix, of course, or sort of this row, of course, but we can reuse the x1, x2, or is it K1, K2, and K3 from the previous calculation. So we store these vectors essentially in a cache, which allows us to reuse computations at the expense, of course, of memory, right? You can't have infinite cache, so you need to, the more memory you have, the more cache you can use, the more calculations you can store, but then once you run out of it, you still need to do cache management techniques and so on. Right, we can reduce the size in the model footprint in memory by using a lower precision, right? In the end, what we're doing is multiplications and additions plus some nonlinearity, but when we sample from the model, in the end, we're just looking at the probability distribution, and we might, even only if we're doing a greedy sampling, we might only care about what is the maximum probability, so we don't really care about the fine correctness of the sort of each of the values. All we care is that one value is bigger than the other one, and for that we don't need that much precision. So there's methods that can reduce sort of the precision of your model from 32-bit to 16 to 8 down to 4-bit, which then means that your model requires less memory to load, and which then allows you to load these memories in a consumer-grade GPU. And when you want to fine-tune them, you can combine this quantization with a essentially adapter approach, where rather than training all the billions of parameters of the language model, you just essentially build small shims in between the layers for the query key and value matrices in order to train only a small subset of the parameters. Now, this, again, I guess the bottom line here is that all these things play together, and they're all well implemented in the modern training and inference frameworks, and you can use them directly, more or less out of the box. So to summarize, what we have covered so far is sort of how we represent text, so what is words, tokenization, how can we represent it with embeddings or using language modeling. We looked at how we can build next token prediction machines. These are essentially, we looked at RNNs, went over to transformers. We looked at how we can train them and how we can sample from them in order to generate new text. We have then looked at what are sort of the ingredients to go from these next token prediction machines into helpful general purpose sort of technologies or assistants. What we didn't cover are different architectures, but they exist. So encoder was developed in parallel with the sort of decoder-only causal language model. There's encoder-decoder models such as T5. We didn't look at multi-model models, because if we had to cover all of these things, we would have probably have a winter skill only on LLMs, right? But if you're interested in that, lava is a good keyword. If you want to look at the paper, it's a quite smart way of using, again, the next token prediction to incorporate representations of images. We haven't looked at retrieval augmented generation, but we will later today. We haven't looked at architectural changes that did actually make it into the sort of base transformer architecture, such as a mixture of experts. But we definitely didn't look at this other architecture, such as state space models or spiking neural networks, because, well, they're not really being used, but they can be used with model distillations, where we have big models and we distill them to more sort of smaller and more efficient models, potentially if you want to run them on on a watch or on your phone, or on some more sort of constrained hardware. So specifically, these spiking neural networks are more hardware efficient. We haven't looked at how we scale from a few tokens to 128,000, which is a commonly sort of used size today. So these are other embedding techniques, as well as approaches such as dilated attention or sliding attention, and generally how we deal with big context windows. And we haven't looked at safety and evaluation and general sort of benchmarking of LLMs in depth. I just mentioned sort of a couple of things, right? But I think we will have a couple of sessions on AI safety and hallucinations, which might cover some of these topics. So to summarize, language modeling is the core objective. In the end, there's always just a next token prediction, right? Everything else is built on this, either directly or with reinforcement learning. Using embeddings enables generalization. So even in LLMs, we sort of implicitly learn the embeddings, but to turn text into numbers, text into vectors, we still use embeddings at the first stage, right? We use transformers instead of RNNs because of their ability to scale with the compute and their effectiveness. And the scale is what makes these LLMs successful, right? So the more data and more parameters, more compute we have, the better performance we obtain, and we can predict this to a certain degree. There are 3 training stages of modern LLMs: pre-training, instruction tuning, and aligning, which sort of contributes to different capabilities. And overall, we also briefly covered efficiency techniques to make sure that all these big LLMs are also sort of usable from a user perspective, that you can run them on your computer, and that you can train it for your own tasks if you wanted to. So this concludes the first part of the lecture. Thank you very much. Do we do questions?
Hi, thank you for the presentation. It was amazing. I just have a quick question. How does modern LLMs handle typos in the prompts? Because I can say that for one word, you can misspell a character, and then in a sentence, you can also misspell a character. How does LLMs handle with the typos in prompts?
So, surprisingly robust, again, because the representation of a token with a typo, you would get a slightly different tokenization, right? But the representation would be similar. The reasons for this, number one, is because you encounter typos in the pre-training data, right? It's what, 60% web crawl. No one types perfectly on the internet, right? So you encounter typos. So just by diversity of the training sort of corpora, you learn to deal with this. But also, so you could probably craft an adversarial example just by using typos and sort of word perturbations, which then leads to a weird and unexpected behavior. So sort of the average case, yeah, you do 1-2 typos, probably okay. If you encode so many typos that you can barely understand what's being meant, you can adversarially craft and sort of perturb the prompt until the LLM starts behaving in a way that is sort of not expected, right? And I guess we will learn something about that later, about when we talk about safety and sort of hallucinations and in these sessions.
I have this question that when we have a chatbot, what changes do we make to the model architecture so that it calculates the multi-line attention from the previous transient? I mean, we need some context from that window as well, but if it is not a part of a single prompt, how do we make that into a prompt?
Okay, so the question was how we can incorporate the previous history of the conversation into the chatbot's response. And the answer is, well, like that, right? So in the end, what you do is you just take the user's input, in this case, this input, and you just append it to the tokenized conversation, right? Then you take the assistant's response and you append it again. So when the user again types something, you just append it here, right? So, and so on and so on and so on, until you run out of your context window. And then there are some different methods how to deal with that. The easiest one is you just sort of truncate, right? You forget about what happened before. You could run a summarization model to summarize the whole context and give it as an external memory access. This is something that Vijay will talk about later today. Or you sort of just, you drop some messages which you think are less relevant. Or you can also drop some of the, again, you will hear about that more in the second section, some of the sort of reasoning traces or some of the intermediate steps that the assistant used in order to arrive at the final answer. Does that answer your question?
Thank you for the wonderful lecture. And I have a bunch of different doubts, but one of the major of them is, how do we enforce grammar validation and grammar match while decoding? So like, if you look at toy GPTs that we make, they only give you normal text, normal string output. But any open source model or closed source model that we look at, they give you markdown responses. So how does that happen? How do we train the decoder? How do we enforce the decoder to do that? Do we enforce the model to do that? How does that exactly happen?
So I think in the example of Markdown specifically, I would argue that it was specifically instruction tuned to produce Markdown, right? I think there's just, so for example, Llama and obviously all the OpenAI, Claude and Gemini models, they're closed source. You don't know what they've been trained on. Llama, you don't know what the instruction tuning set was. Probably a lot of crowdsourced annotations of, here's a question, please write a nice markdown, right? And then the model sort of learns that the preference is to write markdown. Similarly, you could get that from the preference alignment. You just generate normal text and markdown formatted text, and then you ask the audience which one is better. Most people would probably like the nicely formatted one. If you want to enforce it, you can. You would need to use one of the libraries here that I mentioned before. Right, yeah, like outlines. They usually operate with final state automata. But that being said, like Markdown is not a very
No, so it's not complicated. But so Quen, for example, Quen and DeepSeek, they have their everything open source, but nowhere explicitly in the training corpus or anywhere do we have that give only markdown. So even if when you're asking one-word questions, say a normal addition or one-word answers, we will always in the terminal also give you the 3 colon answer 3 colon. So markdowns are enforced. So in the decoder stage, how exactly the model learns representation?
Yeah, so I don't think it's enforced. Again, it might come also from the pre-training corpora. There's a bunch of markdown stuff, like all the GitHub documentation is markdown, right? It might come through preference alignment, that people just prefer markdown over non-formatted text. I don't think the model, like if you load the Chiwen or the DeepSeek models, if you have the GPU to load DeepSeek, right, you will see that if you load it in VLLM or in Hugging Face, like your own inference loop won't have these enforced, and still it would generate something that is sort of markdown, looks like markdown, that you can then render, right? Does that answer your question?
Not really, no.
Okay, so what kind of answer would you like to hear? I think.
I mean, so I'm not able to understand that by in a simple decoder, how are we able to enforce formats?
We're not enforcing formats for Markdown specifically. If you want to enforce JSON, for example, JSON is without all the comments and so on, is a context-free grammar, right? And then you can use a finite state automaton with backtracking in order to make sure that the next token probabilities when you generate sort of a sequence of tokens are either compliant with the sort of the context-free grammar for JSON, or once you generate it far enough that you can't anymore, you need to backtrack and start generating in a different branch, right?
Okay, that makes a lot of sense.
Yeah, so that's for stuff like JSON. Again, it is worth saying that you can enforce these, but if the model hasn't seen that during training, then you generate something like very, tokens that are not very often encountered during training, and then because when you generate, you take what you generated as part of the context, you then generate the next token based on a context that has been not encountered in training before, and that might give you sort of very weird probabilities for the next tokens. So yeah, JSON, yes. Markdown, probably just because of the way the data looks during training. So there is no, not that I know of, there is no explicit constraint for Markdown.
So the formats are just the probabilities are normalized according to the FSM.
No, yes. So what you get, I think, where was that is here, right? You can implement arbitrarily complex rules to meddle with the probabilities. So the model will always give the probability that it predicts, but then you can always change it, right? So if it doesn't satisfy the regex, you can change the probabilities so for those tokens that don't satisfy the regex or the CFG, you can set them to 0. For those that do, you keep them or boost them, right? If you generate somewhere where you cannot sort of, with all of a sudden all of the probabilities are 0 until you haven't finished the regex or the CFG, you need to backtrack to a point where you can continue reasonably, and then you take a different branch, right? So this is essentially a formal logic kind of thing, right? So it's basically generation with backtracking, yeah. That's why if you use some of the more complicated constraints, it takes a very, very long time to generate, because it sort of runs into paths that you cannot complete the grammar rule with the current probabilities, so it has to backtrack, take the different path, and so on and so on.
Another question, in the reinforcement learning part of the lecture, say for example I'm using ChatGPT, and ChatGPT gives me 2 responses and then asks for my preference.
Mhm.
If I get the exact same prompt with the exact same context, say in a different chat, I am not assured to get one of the two responses that I had previously gotten. Now, I'm sure they would not be fine-tuning the model real time. So they're using both of these instances, have the same model weights. While training, OpenAI has, for this prompt, if this is the response, then good. If this is the response, then bad. They have this data. But while during the inference process for background, how are they able to enforce that the output will be one of these two? Because again, the decoding is a discrete, non-differentiable stochastic process.
Okay.
How are they able to then operate onto this, or for any other model?
Sure. So the output, so you get multiple options. You don't really say that whenever I get this prompt, I want exactly this output, right? It's not like that. You just get these preferences. So you say, okay, this output, for the same prompt, this output is better than that output. And then you'd use that to train a model that then when you sort of have similar inputs and possible outputs can rank them. And then you use that with reinforcement learning or DPO in order to update the model, basically to push it more towards the preferred inputs and less towards the dispreferred. Again, because these are all embeddings and all based on similarity, it will then act when it gets similar prompts. It will generate something more similar to the preferred prompt, right? It's not a one-to-one mapping. They don't do it like that.
The loss is on the similarity score of the output to preference rather than exact mapping.
No, the loss for
PPO. So again,
for PPO.
yeah, so I have a model, and after tokenization, tokenization is a discrete process. It's not differentiable.
Right.
We have two instances. I gave an option. I got two outputs of output A, output B. Let's say our output A is better than output B.
Mm-hmm.
This is a preference that I as a human annotator gave. Now I have a data. A is for prompt B, context C. A is good, B is bad. Now say I have to use this and better my model, fine-tune my model. But I'm not assured given P comma C, I will get A or B. I may get something like C or D or.
Yeah, but that's why you use the models, right? So a model takes as input a sentence and it gives you a score. Now, if the sentence is somewhat similar to your example in the training set, and you trained it on it, you will get a slightly similar output, right? But because these are essentially embeddings, you're not dealing with.
I'm able to explain my question very well.
Maybe it's better if we can talk offline. Coffee time?
Yeah, I think you should.
Okay. Thanks.